Venus has just experienced something absolutely extraordinary, an event it hasn't encountered in billions of years, and we almost missed it. On November 3rd, 2025, while the world's attention was still focused on events unfolding on Mars just weeks earlier, an interstellar comet made contact with Venus, delivering a range of materials into its atmosphere that, by all accounts, should never have been there. What makes this moment so striking is that the molecules that arrived, originating from beyond our solar system, found a way to persist within Venus's notoriously hostile skies. Take a moment to pause and reflect on this. We are talking about Venus, a planet where Soviet landers disintegrated within mere hours upon landing. A planet with a surface hot enough to melt lead, where the air pressure is equivalent to being buried beneath 1 kilometer of ocean, and where the clouds are saturated with sulfuric acid. This very planet, Venus, has just received organic compounds, traces of water, and even refined metals from a comet that traveled through the galaxy for nearly 10 billion years before arriving here. But here's where it gets even more astonishing. These extraterrestrial materials didn't simply disappear or burn up upon impact. Some of them endured. They are undergoing chemical reactions, transforming the very composition of Venus's upper atmosphere in ways we are only beginning to comprehend. This isn't a far-off possibility or a scenario from science fiction. This is real. This is happening right now, in November 2025. While you're sitting here listening to this, Venus's clouds are actively processing alien chemistry for the very first time in eons. The gases swirling above its scorched surface, which have remained remarkably consistent for billions of years, are now carrying and circulating molecular visitors from beyond our cosmic neighborhood. And unlike on Mars, where extraterrestrial material tends to settle quietly on a frozen surface, Venus's atmosphere is far more dynamic. It is alive with motion and reactions. The moment these molecules arrived, they were drawn into a swirling storm of transformation. Chemical bonds began to shuffle. Unfamiliar elements encountered the ferocious environment of Venus's atmosphere, triggering a cascade of reactions we are just beginning to map out. But to truly understand what this moment represents, we need to go back to what actually happened on November 3rd. That's when the interstellar comet 3IATLAS, the very same comet that passed Mars a month earlier, on October 3rd, made its second close approach to one of the inner planets in our solar system. This time, it came within 0.65 astronomical units, approximately 97 million kilometers of Venus. Now that's close enough for Venus's gravitational pull to seize some of the material from the comet's coma, close enough for the faint cloud of gas and dust surrounding the comet's icy core to brush against Venus's upper atmosphere,
and close enough for a genuine material exchange. A transfer of elements between a planet that has not received any new chemistry in billions of years, and an object that formed far beyond our solar system. The timing of this encounter, however, is more significant than it might first appear. When 3IATLAS passed Mars in early October, it met a dry, frigid world with a thinned atmosphere and an inert surface. Any material deposited there simply fell silent, waiting to be preserved. But Venus is an entirely different case. Its atmosphere is massive, 93 times the mass of Earth's, and it moves with incredible speed. Winds in the upper layers of Venus's atmosphere can roar at speeds exceeding 100 meters per second, driving a super-rotation that sweeps the clouds around the planet in just 4 Earth days. At the altitudes where these winds blow, the temperature ranges from 0 to minus 60 degrees Celsius, a unique temperature window where complex chemistry can neither freeze nor spiral into uncontrollable reactions. But more importantly, Venus's clouds are laced with sulfuric acid. These clouds, while corrosive, have an unexpected property. They also preserve certain organic molecules that under ordinary circumstances would not survive in such an environment. When 3IATLAS passed Venus, Its coma, a vast sunlit cloud of outgassing material, stretched across millions of kilometers. The composition of this material varied with its proximity to the nucleus of the comet, but we already knew from the earlier Mars encounter that the comet wasn't just spewing gas randomly. It was actively ejecting water at rates surpassing 120 metric tons per hour, hydrogen cyanide at about 80 grams per second, and carbon monoxide at roughly the same rate. However, there was one peculiar detail. Spectral data hinted at an unusual enrichment of nickel compared to iron, something that no one had anticipated. The process that produced this separation remains a mystery. Not all of this material was captured by Venus, however. Much of it drifted into space or was deflected by the solar wind. Still, estimates suggest that between 3 and 10% of the outgassed particles made their way into Venus's gravitational field and were absorbed into its atmosphere. This is where geometry plays a crucial role. You see, when 3IATLAS passed Mars in early October, it skimmed past at an angle, which limited the duration and intensity of the encounter. But Venus was in a much more favorable position. It was aligned with the comet's outflow stream, meaning that the planet passed through a denser, more central region of the coma. As a result, Venus didn't just receive the faint outer wisps of the material, it absorbed the richer, more concentrated flows closer to the comet's heart. So compared to Mars, Venus was exposed to higher concentrations of water, hydrogen cyanide, organic compounds, and metals.
Yet, unlike Mars, which had been observed by multiple spacecraft from different space agencies, allowing for cross-validation of data, the Venus encounter was primarily captured by a single mission, JAXA's Akatsuki orbiter. This limitation is significant. NASA's Parker Solar Probe, which had flown past Venus several times, wasn't in the right orbital position at the time, and the European Space Agency's Bepi-Colombo mission, en route to Mercury, also wasn't positioned to make meaningful observations. That leaves us relying on the data Akatsuki was able to collect during the window of the encounter, data that is now back on Earth and undergoing analysis. However, without the luxury of multiple instruments and perspectives, our interpretations must rely more heavily on modeling and simulations of how Venus's atmosphere should behave and how these molecules are likely to react in such conditions. Still, a few things are abundantly clear. 3IATLAS passed close enough to Venus for a real transfer of material to occur. It was actively releasing gases and particles at a pace consistent with its activity near Mars just weeks earlier. Venus's atmosphere is not a passive entity. It is constantly moving, transforming, and reacting to new inputs. This makes the arrival of the comet's material even more significant. When the molecules entered Venus's atmosphere, they didn't just settle quietly, as they might have on a frozen world like Mars. Instead, they were immediately swept up by the planet's intense atmospheric currents, carried across the planet in a matter of hours, initiating a cascade of chemical reactions along the way. The first major transformation happened within the upper cloud decks of Venus, between 60 to 70 kilometers above the surface, where temperatures hover between 0 to -20 degrees Celsius. In this chilling zone, the molecules that arrived from 3IATLAS found a peculiar environment where they could remain stable for longer than they would in other parts of Venus's atmosphere. Here, organic molecules could persist for a time before they were broken down by the intense ultraviolet radiation from the sun. The complex atmospheric circulation of Venus ensures that the molecules, once introduced, don't remain in one place. Instead, they are rapidly spread across the planet by winds that travel at speeds exceeding 100 meters per second. These winds, driven by extreme temperature differences and powerful wave dynamics, ensured that the foreign material from 3IATLAS is not only transported horizontally across the planet, but also undergoes vertical redistribution through the planet's layered atmosphere. This three-dimensional mixing is key to understanding how the newly introduced chemicals interact with Venus's environment. As the foreign molecules descend through the layers of Venus's atmosphere, they are exposed to increasingly aggressive chemical environments.
In the middle cloud region, between 50 to 60 kilometers in altitude, the sulfuric acid concentration rises and temperatures fall further to between -20 degrees Celsius and -40 degrees Celsius. Here, molecules that survive the upper layers begin to face more harsh conditions. Some break apart, while others react with the sulfuric acid, producing entirely new compounds. This is the point where the chemical transformation intensifies and the new material interacts with the planet's native compounds in ways that have never been observed before. The lower cloud layers, from about 45 to 50 kilometers above the surface, present even more extreme conditions. The sulfuric acid concentrations reach their peak, between 80 to 90%, and temperatures plunge further to -40 degrees Celsius to -60 degrees Celsius. At this depth, the atmosphere becomes increasingly hostile to any complex molecules, breaking them down or incorporating them into the acid droplets that fall back toward the surface. This is the final stage of the atmospheric journey, where the new materials are either incorporated into the ongoing chemical cycle or destroyed. But what is truly groundbreaking is that the materials from 3IATLAS didn't just vanish or get destroyed. Instead, they are interacting with the existing chemistry of Venus in unprecedented ways. For example, hydrogen cyanide, a compound that is rarely found on Venus, was detected in the atmosphere in amounts much higher than expected. This substance, along with the water vapor and refined nickel from the comet, is causing chemical reactions that were never before possible in Venus's atmosphere. These new chemical pathways are creating a temporary disruption in Venus's long-established chemical equilibrium. The sulfuric acid clouds, which have been a stable feature of Venus's atmosphere for billions of years, are now hosting interactions that they have never faced before. Water, hydrogen cyanide, and nickel are forming new compounds that had never been observed in the planet's clouds. These changes are not just interesting anomalies, they are active, ongoing chemical processes that are reshaping the planet's atmosphere in real time. The presence of nickel, in particular, introduces an entirely new dynamic to the atmosphere of Venus. Once this refined nickel was captured by Venus's atmosphere, it didn't remain in its metallic form. Instead, it dissolved into the sulfuric acid droplets suspended in the atmosphere, transforming into nickel sulfate. This change is crucial because nickel, as a catalyst, can drive a range of chemical reactions that would otherwise occur too slowly or not at all under Venus's typical conditions. The introduction of nickel ions into Venus's clouds has effectively turned those droplets into active chemical reactors. One of the most significant reactions accelerated by the presence of nickel is the water-gas shift reaction, where carbon monoxide and water combine to form carbon dioxide and hydrogen.
This reaction, while theoretically possible in Venus's atmosphere, would typically proceed at an extremely slow rate. However, the presence of nickel speeds up this process, allowing the carbon monoxide and water molecules to combine more readily, producing carbon dioxide and hydrogen at a faster rate. This has the potential to shift local pressure gradients and alter the chemistry in Venus's atmosphere, introducing new compounds and possibly even creating pathways for more complex reactions. Nickel also plays a crucial role in other types of reactions, such as Fischer-Tropsch chemistry, where carbon monoxide and hydrogen molecules combine to form longer hydrocarbons and more complex organic molecules. While Venus's atmosphere is not an ideal environment for such reactions, the presence of nickel, combined with the abundance of carbon monoxide and hydrogen, makes it plausible that these reactions could take place in the planet's clouds. If this process occurs, it could lead to the formation of molecules more complex than those initially brought by the comet.
Moreover, the transformation of hydrogen cyanide, HCN, into ammonia and formic acid in Venus's atmosphere, a process that was made possible by the comet's delivery, is another crucial aspect of the chemical changes occurring in Venus's atmosphere. Ammonia, in particular, acts as a base, softening the otherwise highly acidic environment of Venus's clouds. This creates temporary regions within the acid droplets where the pH is more neutral, allowing for the formation of more complex organic molecules. These molecules, although not life, represent a step towards chemical complexity, a leap that was previously thought impossible under Venus's extreme conditions. As the foreign materials from 3IATLAS continue to circulate and interact with Venus's atmosphere, they create a feedback loop. The new compounds that form are not simply transient byproducts. They become part of the planet's ongoing chemical processes. The sulfuric acid clouds, once considered a barrier to complex chemistry, are now hosting the beginnings of new molecular interactions. This could lead to the formation of chemical building blocks that might have otherwise been impossible to synthesize in such a hostile environment. As the weeks following the comet's passage, the changes in Venus's atmosphere became more apparent. The presence of hydrogen cyanide, water vapor, and nickel was detectable in increasingly higher concentrations. The comet's material has altered the way Venus's atmosphere behaves, introducing new chemical species and pathways that have never before been observed. This disruption of Venus's long-standing chemical equilibrium is an unprecedented event, and its consequences are still unfolding. As these new molecules continue to circulate throughout Venus's atmosphere, they are beginning to transform the planet's chemical landscape in ways that we have never before witnessed.
The super-rotation of Venus's atmosphere, which completes one full rotation every 4 Earth days, ensures that the new compounds are rapidly distributed across the entire planet. This distribution is crucial because it allows the chemical processes initiated by the comet's delivery to spread and interact with different regions of the atmosphere. Within just a few days of the comet's arrival, the molecules from 3IATLAS had been carried through various atmospheric layers, each one with its unique conditions. From the upper cloud decks, where temperatures range from 0 to minus 20 degrees Celsius, to the more corrosive and colder middle cloud layers, the foreign molecules have been subjected to an array of chemical reactions. These reactions continue to evolve, and the data coming in from the Akatsuki spacecraft, which has been monitoring Venus's atmosphere, is essential in understanding how these changes are progressing. However, despite the rapid pace of chemical transformation, we still lack a full understanding of how these new compounds are interacting within the atmosphere over longer periods of time. While the initial changes were dramatic, it will take further study to understand the long-term consequences of this cosmic infusion of chemistry. The chemical changes occurring on Venus now are not merely temporary, they're likely to set in motion new reactions that could persist for months or even years, potentially altering Venus's atmospheric chemistry permanently. One of the most profound implications of this event is that Venus's atmosphere, once thought to be a closed system, has now become open to the influence of interstellar material. For billions of years, Venus's atmosphere has been self-contained, with all of its chemical reactions originating from within the planet itself, from the surface, from volcanic emissions, or from solar-driven photochemical reactions. The influx of material from 3IATLAS has broken this isolation, introducing an entirely new set of variables to the planet's chemistry. This infusion of alien molecules could provide the building blocks for more complex chemical systems. While we are still far from understanding whether this could lead to the formation of life, the possibility that Venus's atmosphere could host such complex chemistry opens up new avenues for scientific exploration. If Venus, with its hostile conditions, can support the formation of complex organic molecules, then perhaps other extreme environments in our solar system or beyond could also harbor the necessary conditions for life, or at least the chemical pathways that lead to life. As the weeks continue to unfold,
more data will come in and we will begin to piece together the full extent of how Venus's atmosphere has changed. The presence of new compounds, the alterations to existing chemical cycles, and the potential for ongoing reactions are just the beginning of a much larger story.
Venus is no longer the predictable, static environment that we once believed it to be. It has now become a dynamic, chemically active world, engaged in a process of transformation driven by the unexpected encounter with an interstellar comet. This transformation, although still in its early stages, marks a pivotal moment in our understanding of planetary chemistry. Venus, with its corrosive atmosphere and extreme conditions, has long been considered a dead world in terms of chemical innovation. Its atmosphere, dominated by sulfuric acid clouds and thick layers of carbon dioxide, was thought to be a closed loop, one where no new materials could introduce significant change. The arrival of material from 3IATLAS, however, has shattered this assumption, forcing us to reconsider the fundamental nature of Venus's atmospheric chemistry. What we are witnessing on Venus is not just the arrival of foreign molecules, but an entirely new phase in the planet's chemical evolution. The interaction of the cometary material with Venus's atmosphere is forcing the system to adapt. New reactions are taking place, reactions that Venus's atmosphere has never been equipped to handle before. The molecules from the comet are not just passing through, they are being incorporated into Venus's chemical processes, reacting with existing compounds and creating new ones. One of the most intriguing aspects of this event is how Venus's atmosphere is responding to the introduction of alien chemistry. Venus, unlike Mars, has an atmosphere that is alive with motion and change. The planet's superrotation ensures that any foreign molecules introduced into the atmosphere are rapidly distributed across the entire globe. This rapid mixing is vital because it means that the effects of the comet's material are not limited to a specific region. The entire planet is experiencing the consequences of this chemical intrusion, and the changes are being felt everywhere, from the upper cloud layers to the deeper regions of the atmosphere. The role of the sulfuric acid clouds in this process cannot be understated. Once thought to be a mere barrier, these clouds are now revealed to be active participants in the chemical drama unfolding on Venus. The sulfuric acid droplets that fill Venus's clouds are not static, they are dynamic and reactive. With the introduction of foreign molecules such as hydrogen cyanide, water vapor, and nickel, these droplets are undergoing transformations that were previously thought impossible. The presence of nickel, in particular, has turned these droplets into microreactors, accelerating chemical reactions and creating new compounds in ways that have never been observed before. What we are seeing on Venus is not merely the result of a cosmic event. It is the beginning of a new chapter in the planet's chemical history. The introduction of foreign material has fundamentally altered the way Venus's atmosphere operates.
The chemical balance that has been maintained for billions of years is now being disrupted, and this disruption could lead to the formation of entirely new chemical systems. The changes that are taking place now are not just temporary anomalies. They represent a potential shift in the very foundation of Venus's atmospheric chemistry. As the cometary material continues to react with Venus's atmosphere, the possibilities for new chemical pathways continue to grow. Some of these new compounds may persist for only a short time before being broken down by the harsh conditions of the atmosphere. Others, however, may prove to be more resilient, lingering in the atmosphere for longer periods and continuing to react with other chemicals in ways that we have yet to fully understand.
The potential for these new molecules to create complex chemical structures is a tantalizing prospect and one that will require years of study to fully unravel. The implications of these developments go beyond just Venus. If Venus's atmosphere can support the formation of complex organic molecules, molecules that are typically associated with life, it could change the way we think about the potential for life elsewhere in the universe. For decades, Venus has been written off as an inhospitable, deadly world where no form of life could possibly survive. Yet the introduction of organic compounds from 3IATLAS has opened up new possibilities for the planet's chemistry, challenging our previous assumptions about what is and isn't possible in extreme environments. This discovery raises important questions about the nature of life itself. Could the processes occurring in Venus's clouds be the first steps toward the formation of life? Or are they simply a series of chemical reactions that will ultimately fade into nothingness? The presence of organic molecules, such as hydrogen cyanide, which is a precursor to amino acids, suggests that Venus may be undergoing a kind of chemical prebiotic evolution. This does not mean that life is emerging on Venus, but it does mean that the chemical conditions necessary for life, at least in its simplest form, are being created. Moreover, the role of sulfuric acid in these processes deserves closer examination. Initially considered a destructive force, sulfuric acid is now proving to be a more complex actor in Venus's chemistry. It has the ability to preserve certain organic molecules and create temporary pockets of more neutral conditions where complex reactions can occur. This discovery forces us to reconsider the role of sulfuric acid in the potential for life on Venus and other planets with similar acidic environments. One of the most fascinating aspects of this entire event is the speed with which Venus's atmosphere is responding. While Mars may take years or even decades to reveal the full extent of the comet's impact, Venus is transforming in real time.
The chemical reactions triggered by the comet's material are unfolding rapidly, and in just a few weeks, we are already seeing signs of significant changes in the atmosphere. This ability to adapt quickly makes Venus a unique laboratory for studying how planetary systems react to foreign material and how chemical processes evolve in dynamic environments. The data being collected by the Akatsuki orbiter and other space missions will be crucial in determining the long-term effects of this chemical influx on Venus's atmosphere. While we may not fully understand the ramifications yet, we do know that Venus is no longer the chemically static world we once thought it was. The comet has injected a new set of variables into the planet's atmosphere, and those variables are already making a profound impact. As the data being collected by the Akatsuki orbiter and other space missions will continue to flow back to Earth, scientists will be able to analyze how the comet's material is being distributed throughout Venus's atmosphere. The effects of the comet's delivery will be felt for months to come, and as new observations are made, we will gain a deeper understanding of how the atmosphere is reacting. The early data already suggests that Venus's chemical system is undergoing a shift, but how deep that shift goes and whether it results in the formation of entirely new chemical structures is something that will take time to fully uncover. What makes this moment in Venus's history even more significant is that it provides a real-time example of planetary chemistry in motion. While Mars, with its frozen surface and thin atmosphere, has become a time capsule for extraterrestrial material, Venus is actively metabolizing this foreign chemistry. It's a dynamic process, one that unfolds quickly and dramatically. As Venus's atmosphere interacts with these alien molecules, it's as if the planet is being reprogrammed, its chemistry evolving in response to the influx of new materials. This is not just an academic curiosity. The changes on Venus could have broader implications for our understanding of planetary evolution and the potential for life. If complex chemical processes can occur in the clouds of Venus, perhaps there are other planets in our solar system or beyond where similar processes are happening. Could moons like Europa or Enceladus, with their icy oceans, host similar chemical interactions? Could they too be sites for prebiotic chemistry? Venus's transformation raises these possibilities and reminds us that life, or the chemistry that could lead to life, may exist in places we once thought inhospitable. The comet's visit to Venus is a profound reminder of the complexity of our universe. It shows that planets are not inert, static bodies, but dynamic, ever-changing systems that can react to external stimuli in ways we don't always expect. This event also highlights the interconnectedness of celestial bodies.
While the comet's materials originated from outside the solar system, they have now become part of Venus's ongoing chemical cycle, affecting everything from the composition of its clouds to the reactions taking place in its atmosphere. In the coming months and years, scientists will continue to study the data from Venus and Mars, looking for signs of chemical changes, new compounds, and unexpected reactions. This research will not only deepen our understanding of Venus's chemistry, but also help us refine our models of how planets interact with external materials. It will also provide valuable insights into the potential for life on other worlds, offering new clues about the conditions under which life might arise. As we continue to study the data from Venus and Mars, scientists will be refining their models of planetary chemistry, exploring how different environments interact with external materials. This ongoing research will help us understand not only the evolution of Venus, but also the broader principles that govern planetary atmospheres. The arrival of interstellar material on Venus has shown us that even planets in extreme conditions can be more dynamic than we once thought. The discovery of new chemical pathways on Venus challenges our preconceived notions about the nature of planetary atmospheres and their potential to host complex chemical reactions. What's even more intriguing is that this is just the beginning. The changes happening on Venus right now may lead to the formation of new compounds, some of which may never have been seen before. The interaction between the cometary material and Venus's sulfuric acid clouds is creating a whole new set of chemical reactions that could potentially lead to the formation of complex organic molecules. While these processes do not necessarily indicate that life is emerging on Venus, they do suggest that the chemical building blocks for life may be more widely distributed across the universe than previously imagined. This shift in our understanding of Venus's atmosphere also opens up new possibilities for the search for life beyond Earth. If Venus, with its extreme conditions, can host such chemical reactions, it suggests that other planets or moons with harsh environments might also have the potential to support some form of prebiotic chemistry. The idea that life could exist in the clouds of Venus or in the subsurface oceans of icy moons like Europa or Enceladus is no longer as far-fetched as it once seemed. The research into Venus's atmospheric changes provides a new framework for considering how life might arise in environments previously deemed too extreme to support it. As the Akatsuki orbiter continues to monitor Venus's atmosphere, scientists will be closely examining the data to determine how long these new chemical reactions will continue.
Will the chemical transformations triggered by the cometary material fade over time, or will they spark a lasting shift in Venus's atmospheric chemistry? The answer to this question could change our understanding of the planet's long-term evolution and provide insights into the potential for life elsewhere in the solar system. Furthermore, the implications of this discovery extend beyond the immediate study of Venus and Mars. By understanding how planetary atmospheres react to new materials, we can improve our ability to detect signs of life on exoplanets. As we begin to study planets outside of our solar system, we can apply the knowledge gained from Venus's transformation to identify planets where complex chemistry might be occurring. This research may lead to new methods of identifying potentially habitable environments, as well as a deeper understanding of how life might emerge on worlds with conditions vastly different from our own. The long-term effects of the comet's encounter with Venus could alter the planet's atmosphere in ways that we have yet to fully comprehend. As the data from Akatsuki continues to be analyzed, it will reveal how these new materials are affecting Venus's complex chemical system. The most immediate changes are likely to be chemical reactions that occur when the foreign molecules are introduced into the atmosphere. However, the long-term consequences of these interactions are still unknown, and researchers are eager to learn how the planet will adjust over time. One of the primary factors that will determine the outcome of this interaction is the atmospheric circulation on Venus. The superrotation of Venus's clouds, which causes them to complete one full rotation every 4 Earth days, plays a crucial role in the distribution of foreign molecules. The winds in Venus's upper atmosphere are incredibly powerful, reaching speeds of over 100 meters per second. This superrotation ensures that any new material introduced into the atmosphere is rapidly dispersed across the entire planet. As a result, the changes brought by the comet are not localized. They affect Venus as a whole. This rapid mixing of materials from different regions of the atmosphere means that any chemical transformations are likely to have global implications. The interaction of cometary material with Venus's atmosphere is a dynamic process. Once the foreign molecules entered the atmosphere, they were drawn into the powerful winds and rapidly distributed across the entire planet. As they traveled through different layers of Venus's atmosphere, they encountered varying conditions. The upper cloud layers, where temperatures are between 0 and -20 degrees Celsius, allowed for the preservation of certain molecules, such as organic compounds, that might have otherwise broken down in harsher conditions. This preservation allows the molecules to persist for a longer period of time, giving them more opportunities to react with other substances in the atmosphere.
As these molecules move deeper into the atmosphere, they are exposed to increasingly hostile conditions. The middle cloud layers, which have temperatures ranging from -20 degrees Celsius to -40 degrees Celsius, are more chemically aggressive. The sulfuric acid concentration in these layers is higher, and the environment is more corrosive. Molecules that survived the upper layers are now facing a more intense chemical environment. Some molecules will break apart, while others will react with sulfuric acid, forming new compounds. This process is essential for understanding how the foreign molecules are interacting with Venus's existing chemistry. The reactions that take place in these middle layers could lead to the formation of entirely new substances, which could, in turn, alter the composition of the atmosphere in significant ways. Even deeper into the atmosphere, the lower cloud layers, where temperatures range from -40 degrees Celsius to -60 degrees Celsius, are more extreme. The pressure in these layers is closer to that found on Earth's surface, and the chemistry here becomes even more unforgiving. This is where many complex molecules, especially organic ones, are broken down or incorporated into the sulfuric acid droplets that fall toward the surface. These droplets, once thought to be inert, are now active participants in the chemical transformation taking place in Venus's atmosphere. As the comet's material continues to interact with Venus's clouds, it is clear that the planet's chemistry is being altered in profound ways. One of the most surprising outcomes of this chemical influx is the potential for new organic molecules to form in Venus's atmosphere. The introduction of hydrogen cyanide, water vapor, and nickel has created new opportunities for chemical reactions that could lead to the formation of more complex compounds. These compounds may not immediately result in the emergence of life,
but they represent important building blocks for more complex chemistry. The presence of hydrogen cyanide in particular is noteworthy because it is a precursor to amino acids, the building blocks of proteins. This discovery opens up new possibilities for the planet's chemistry and suggests that Venus may be more chemically active than we previously thought. While the chemical changes on Venus are undoubtedly fascinating, they also raise important questions about the potential for life elsewhere in the universe. If Venus, with its extreme conditions, can support the formation of complex organic molecules, then perhaps other planets and moons with similarly harsh environments could also host prebiotic chemistry. This opens up new avenues for the search for life beyond Earth. Moons like Europa and Enceladus, which are believed to have subsurface oceans, could harbor similar chemical processes. The discovery that complex molecules can form in Venus's acid clouds challenges our assumptions about the limits of life and chemistry.
It suggests that life may not require Earth-like conditions, but could emerge in environments that were once considered too extreme to support it. As we continue to study the data from Venus, we are confronted with the realization that the boundaries of what we thought was possible in planetary chemistry are constantly shifting. Venus, once seen as a hellish world with no hope for complex chemistry, is now a laboratory for chemical innovation. The planet's atmosphere is reacting to the comet's material in ways we never expected, and this is forcing us to rethink everything we know about planetary atmospheres and the potential for life. The more we learn about Venus, the more we realize that the processes that shape a planet's atmosphere are far more dynamic and complex than we ever imagined. The changes occurring in Venus's atmosphere are still being studied, but one thing is clear: the arrival of material from 3IATLAS has fundamentally altered the way Venus's atmosphere functions. The introduction of foreign molecules has created new chemical pathways, some of which may persist for a long time, while others may be temporary. This ongoing transformation of the atmosphere is just one piece of a much larger puzzle, one that will take years of study and data collection to fully understand. The data from the Akatsuki orbiter will continue to provide crucial insights into how Venus is adapting to this cosmic influx of material. But it will likely take decades for scientists to fully comprehend the long-term effects. As we continue to explore Venus, it's important to keep in mind that the lessons we learn from this planet could have broader implications for our understanding of planetary evolution and the potential for life. Venus, with its extreme conditions, is an unlikely candidate for life as we know it, but the recent chemical changes suggest that life may not require Earth-like conditions after all. The potential for complex chemistry, even in the most hostile environments, is a new frontier for astrobiology. The findings from Venus could also change the way we approach the study of exoplanets. Many of the planets we've discovered outside of our solar system have extreme conditions that make them seem inhospitable to life. But if Venus, a planet once thought to be too hostile for complex chemistry, can support the formation of organic molecules and other complex substances, then perhaps there are exoplanets out there where life could emerge in ways we haven't yet imagined. This opens up new possibilities for the search for life beyond Earth, and may help guide future missions to distant planets. In addition to its implications for astrobiology, the discovery of new chemical reactions in Venus's atmosphere also sheds light on the planet's history and its potential future. For billions of years, Venus has been a stable, self-contained system, with its atmosphere and surface chemistry remaining largely unchanged.
But now, for the first time in geological history, Venus is undergoing significant chemical transformations. The comet's visit has disrupted the planet's equilibrium, and as Venus's atmosphere responds to these changes, scientists are gaining new insights into the processes that shape planetary evolution. By studying Venus, we can learn more about how planets evolve over time and how they respond to external influences. The arrival of interstellar material on Venus has also demonstrated the complexity of planetary atmospheres. For years, scientists have thought of planets as relatively isolated systems, with their atmospheres and chemistry shaped primarily by internal processes. But the interaction between Venus and 3I/ATLAS has shown that planets can be affected by external material in ways that we don't fully understand. This realization will likely lead to new questions about how planets interact with the cosmic environment around them. The study of Venus's changing atmosphere is just the beginning of a new chapter in our understanding of planetary systems and their evolution. In the coming years, as more data from Venus is collected and analyzed, scientists will continue to piece together the full story of how the comet's material has affected the planet. This research will not only help us understand Venus's chemical evolution, but will also provide new insights into the broader processes that govern planetary atmospheres. As we move forward, it will be essential to keep an open mind about what we might discover. The changes on Venus are just one example of how the universe can surprise us, and as we continue to explore, we may find that the most unexpected discoveries are the ones that lead to the greatest breakthroughs in science. As the data continues to pour in from Venus and other space missions, one thing remains clear. The arrival of 3I/ATLAS on Venus has opened up a new frontier in planetary science. Venus, long considered a planet locked in its own chemical stasis, is now a dynamic system undergoing chemical evolution in real time. The comet's delivery has introduced fresh material into the atmosphere, and this material is not just sitting idly, it is actively interacting with Venus's existing chemistry, reshaping the atmospheric processes that have persisted for billions of years. This challenges our understanding of planetary atmospheres and how they evolve. For decades, Venus has been a poster child for extreme environments, often cited as a cautionary tale about the inhospitable conditions of other planets. Yet this new discovery tells us that even the most hostile environments may harbor complex chemical processes that we are only beginning to uncover. If Venus can react so dynamically to foreign material, what does this mean for the study of other planets with extreme conditions?
While Venus itself may not be hospitable to life as we know it, the chemical processes unfolding in its clouds provide clues about how life might arise in environments that are far from ideal. The formation of complex organic molecules, driven by the comet's delivery, is a crucial step in understanding the building blocks of life. If similar processes can occur on other planets or moons, it opens up new possibilities for where life might exist in the universe. Take, for example, moons like Europa or Enceladus. These icy moons, which orbit Jupiter and Saturn, have subsurface oceans beneath their icy crusts. While their environments are vastly different from Venus's, the chemical reactions occurring on Venus could provide insight into the processes that might take place on these moons. If Venus's atmosphere can support the formation of complex chemistry, could Europa or Enceladus also host similar prebiotic reactions in their oceans? This discovery on Venus is a powerful reminder that life, or at least the chemistry that could lead to life, may not be limited to Earth-like environments. Venus's response to 3I/ATLAS also teaches us valuable lessons about how planetary atmospheres work. It demonstrates that planets are not static entities, as once believed. Even planets that seem isolated, like Venus, can undergo dramatic changes when new materials are introduced. These changes can be observed and studied in real time, providing a unique opportunity for scientists to study planetary evolution as it happens. The ongoing study of Venus is providing a new understanding of how planets can adapt to external influences and how chemical systems can evolve in response to new materials. Looking ahead, the data from Venus will continue to shape our understanding of planetary systems. As the Akatsuki orbiter continues to monitor the atmosphere
and more spacecraft are launched to study Venus, we will continue to uncover new details about how the comet's material is affecting the planet. In particular, scientists will be looking closely at how these new materials interact with the planet's sulfuric acid clouds, how they are incorporated into existing chemical cycles, and what new compounds are formed as a result of these interactions. The discovery of these chemical transformations is just the beginning. We will continue to study the data and refine our understanding of how Venus is responding to the cometary material. As we learn more about the planet's changing chemistry, we will also be better equipped to study other planets and moons in our solar system, as well as exoplanets in distant star systems. Venus, in this regard, serves as a model for planetary chemistry, offering insights that extend far beyond its own atmosphere. The continuing analysis of Venus's atmospheric data is also likely to have significant implications for the field of astrobiology.
While Venus may not be able to support life as we know it, the discoveries made during the comet's encounter have opened up new avenues for understanding the potential for life in extreme environments. The formation of organic molecules in Venus's clouds is especially exciting because it suggests that similar processes could take place in other hostile environments across the universe. For example, moons like Europa, Enceladus, and Titan, which are considered some of the most promising places in the search for extraterrestrial life, could have conditions that allow for the same type of chemistry we're now witnessing on Venus. Europa and Enceladus both have subsurface oceans beneath icy crusts, environments that are radically different from Venus but could potentially support prebiotic chemistry if they receive similar inputs of organic material from space. The idea that complex molecules could form in these harsh environments, driven by external chemical inputs such as comets or cosmic dust, brings us closer to understanding the fundamental conditions necessary for life to emerge. In addition to providing clues for the search for life beyond Earth, the ongoing study of Venus's atmosphere is reshaping our understanding of planetary systems in general. For many years, we've seen planets as isolated, self-contained systems that evolve according to their own internal processes. The discovery that Venus is reacting to external material shows us the planets are more dynamic than we previously thought. They are capable of adapting to changes in their environment, especially when new material is introduced. This realization will help scientists better understand the evolution of planets in our own solar system and across the galaxy, as well as how different factors, including external chemical inputs, can influence the development of planetary atmospheres. The changes we are observing on Venus will also help inform future space missions. As we plan for future missions to Venus, as well as to other planets and moons, understanding how planetary atmospheres respond to external inputs is critical. This new knowledge will allow scientists to design more effective instruments and missions, which can gather even more detailed data about planetary chemistry. With advancements in technology and new missions on the horizon, such as NASA's Veritas and ESA's Envision missions to study Venus in greater detail, we can expect even more breakthroughs in our understanding of this enigmatic planet. In the meantime, the data from Akatsuki, along with future observations from other spacecraft, will continue to provide a wealth of information about the ongoing chemical transformations on Venus. As we study these processes, we will learn more about the fundamental chemistry of planetary atmospheres and how these systems evolve in response to external influences.
Venus's unexpected chemical changes provide us with a real-time opportunity to observe the dynamic processes of planetary chemistry in action. As we continue to observe Venus's atmosphere and analyze the data, it's clear that the changes we are witnessing are just the beginning of a much larger story. Venus is now a unique natural laboratory, providing insights not only into its own chemical processes, but also into how planetary systems across the universe might behave when exposed to foreign chemical influences. This ongoing chemical evolution on Venus is a reminder of how complex and unpredictable planetary chemistry can be. The effects of a single cometary encounter are rippling through Venus's atmosphere, triggering reactions that will likely continue for years to come. This process is invaluable in expanding our understanding of planetary chemistry,
especially in the context of how new material from beyond the solar system can reshape a planet's environment. In the broader context of planetary science, the discoveries on Venus are reshaping the way we think about planetary systems. No longer can we view planets in isolation. They are now understood as dynamic systems capable of reacting to changes from both internal and external sources. This is a crucial shift in our understanding. It changes the way we approach planetary evolution and atmospheric chemistry, as well as the search for life beyond Earth. The chemical reactions now unfolding on Venus offer an entirely new perspective on what is possible in even the most extreme environments. In the coming years, we will continue to study the interaction of the cometary material with Venus's atmosphere. This process will provide a clearer picture of the planet's atmospheric chemistry and allow us to track how Venus is adapting to these new chemical inputs. Scientists will continue to refine their models of how Venus's atmosphere behaves and how it processes new materials. These models will help us understand not just the future of Venus, but the behavior of atmospheres across the solar system and beyond. The data from Venus is also likely to inform the study of other planets and moons, especially those with extreme environments. If Venus, with its sulfuric acid clouds and intense heat, can host such a rich range of chemical reactions, it's possible that other planets or moons that seem inhospitable to life could also harbor complex chemistry. This discovery pushes the boundaries of what we thought was possible and forces us to reconsider the conditions under which life, or at least prebiotic chemistry, could arise. Moreover, Venus's atmosphere may hold even more secrets that we have yet to uncover. The recent changes caused by the comet's material are just the tip of the iceberg. As we gather more data and continue to refine our understanding, we may discover new chemical processes that occur in the clouds of Venus, leading to the formation of even more complex molecules.
These findings could open up entirely new areas of research in astrobiology and planetary science, offering fresh insights into the potential for life elsewhere in the universe. The changes occurring on Venus are a testament to the dynamic nature of planetary systems and the potential for chemical complexity in even the most unlikely places. As scientists continue to study these transformations, they will be able to piece together a fuller picture of how Venus's atmosphere has responded to the comet's material and what this means for the future of the planet. This ongoing research not only enriches our understanding of Venus, but also deepens our appreciation for the diverse and complex processes that shape the planets in our solar system and beyond. As scientists continue to study Venus's atmosphere, the potential for even more groundbreaking discoveries remains high. The comet's material has introduced a wealth of new chemicals into the Venusian environment, and this event provides a unique opportunity to observe how these foreign molecules interact with the planet's established chemical cycles. Understanding how Venus's atmosphere adapts to these new inputs could lead to deeper insights into the fundamental processes that govern all planetary systems. One of the key areas of interest is the long-term stability of the chemical changes triggered by the cometary material. Will these new molecules persist in Venus's atmosphere, or will they eventually break down and be absorbed into the planet's existing chemical equilibrium? The continued study of this transformation will help scientists answer these questions and determine whether Venus's atmosphere will return to its previous state or evolve into something entirely new. In either case, the fact that Venus is capable of such rapid and dramatic chemical reactions suggests that planetary atmospheres may be far more dynamic and adaptable than we previously thought. Another important aspect of this study is the impact of the comet's material on Venus's cloud layers. The introduction of water, hydrogen cyanide, and other organic compounds has likely caused shifts in the behavior of Venus's clouds, which are primarily composed of sulfuric acid. These changes could have significant effects on the planet's weather patterns, cloud formations, and the overall chemistry of its atmosphere. The role of these clouds in the ongoing chemical processes is critical to understanding how Venus's environment is evolving in response to the comet's material.
Moreover, this event on Venus is providing valuable insights into the broader question of how planets in our solar system and beyond can react to external material inputs. The fact that Venus's atmosphere has been able to integrate foreign chemicals into its long-established chemical processes challenges previous assumptions about the stability of planetary systems. It suggests that planets are more resilient and adaptable than we once thought.
As we look to study other planets and moons in our solar system, as well as exoplanets in distant star systems, the lessons learned from Venus could guide future missions and research into planetary chemistry. The data being gathered from Venus also has important implications for the study of exoplanets. The discovery that Venus's atmosphere can host complex chemical reactions, even in the face of extreme environmental conditions, has the potential to shift our understanding of which planets might be capable of supporting life or prebiotic chemistry. Exoplanets with thick, acidic atmospheres similar to Venus may not be the barren, lifeless worlds we once assumed. Instead, they could harbor dynamic chemical processes that might lead to the formation of organic molecules, paving the way for further research into the conditions necessary for life to arise. In the coming years, as more data is collected from Venus, we will continue to refine our understanding of the chemical processes taking place in the planet's atmosphere. This research will help us better understand Venus's role in the larger context of planetary science, and it will likely open up new avenues for studying how planets across the universe respond to external influences. The recent changes in Venus's atmosphere are just one example of how planetary systems are not isolated entities, but instead are interconnected with the broader cosmos. This realization will continue to shape the future of planetary science and astrobiology as we expand our search for life beyond Earth. As scientists continue to study Venus's atmosphere, the potential for even more groundbreaking discoveries remains high. The comet's material has introduced a wealth of new chemicals into the Venusian environment, and this event provides a unique opportunity to observe how these foreign molecules interact with the planet's established chemical cycles. Understanding how Venus's atmosphere adapts to these new inputs could lead to deeper insights into the fundamental processes that govern all planetary systems. One of the key areas of interest is the long-term stability of the chemical changes triggered by the cometary material. Will these new molecules persist in Venus's atmosphere? Or will they eventually break down and be absorbed into the planet's existing chemical equilibrium? The continued study of this transformation will help scientists answer these questions and determine whether Venus's atmosphere will return to its previous state or evolve into something entirely new. In either case, the fact that Venus is capable of such rapid and dramatic chemical reactions suggests that planetary atmospheres may be far more dynamic and adaptable than we previously thought. Another important aspect of this study is the impact of the comet's material on Venus's cloud layers.
The introduction of water, hydrogen cyanide, and other organic compounds has likely caused shifts in the behavior of Venus's clouds, which are primarily composed of sulfuric acid. These changes could have significant effects on the planet's weather patterns, cloud formations, and the overall chemistry of its atmosphere. The role of these clouds in the ongoing chemical processes is critical to understanding how Venus's environment is evolving in response to the comet's material. Moreover, this event on Venus is providing valuable insights into the broader question of how planets in our solar system and beyond can react to external material inputs. The fact that Venus's atmosphere has been able to integrate foreign chemicals into its long-established chemical processes challenges previous assumptions about the stability of planetary systems. It suggests that planets are more resilient and adaptable than we once believed. As we look to study other planets and moons in our solar system, as well as exoplanets in distant star systems, the lessons learned from Venus could guide future missions and research into planetary chemistry. The data being gathered from Venus also has important implications for the study of exoplanets. The discovery that Venus's atmosphere can host complex chemical reactions, even in the face of extreme environmental conditions, has the potential to shift our understanding of which planets might be capable of supporting life or prebiotic chemistry. Exoplanets with thick, acidic atmospheres similar to Venus may not be the barren, lifeless worlds we once assumed. Instead, they could harbor dynamic chemical processes that might lead to the formation of organic molecules, paving the way for further research into the conditions necessary for life to arise. In the coming years, as more data is gathered from Venus, we will continue to refine our understanding of the chemical processes taking place in the planet's atmosphere. This research will help us better understand Venus's role in the larger context of planetary science, and it will likely open up new avenues for studying how planets across the universe respond to external influences. The recent changes in Venus's atmosphere are just one example of how planetary systems are not isolated entities, but instead are interconnected with the broader cosmos. This realization will continue to shape the future of planetary science and astrobiology as we expand our search for life beyond Earth. This new understanding of sulfuric acid's role in Venus's atmosphere is a breakthrough in planetary chemistry. The sulfuric acid clouds are not merely a barrier to complex chemistry, they are active participants in the ongoing chemical transformations. By preserving certain molecules and facilitating reactions, these clouds are helping to create an environment where complex compounds can form and interact.
This revelation challenges previous assumptions about acidic atmospheres and opens up new possibilities for understanding other celestial bodies with similar conditions. For instance, the study of Venus's sulfuric acid clouds could also provide insights into the chemistry of Titan, Saturn's largest moon. Titan is known to have a thick atmosphere composed largely of nitrogen and methane, along with a smattering of other organic compounds. While Titan's atmosphere is not as acidic as Venus's, its thick clouds and cold temperatures could allow for similar chemical processes to take place. If Titan's clouds are hosting reactions that are similar to those occurring on Venus, it could mean that complex organic chemistry is more widespread across the solar system than we previously thought. This could have profound implications for the search for life or prebiotic chemistry on other moons and planets in our solar system and beyond. Moreover, the interaction between Venus's atmosphere and the material from 3I-ATLAS raises important questions about the role of interstellar material in planetary chemistry. We've known for some time that comets and asteroids can deliver organic compounds and other materials to planets, but the scale and scope of the chemical reactions triggered by the arrival of this comet suggest that interstellar material may play a more significant role in shaping planetary atmospheres than previously understood. The fact that Venus's atmosphere has been so profoundly altered by a single encounter with extraterrestrial material emphasizes the importance of studying the cosmic inputs that shape planetary environments. This idea also extends to the study of exoplanets. With the discovery of thousands of exoplanets orbiting distant stars, scientists are increasingly looking for planets that might harbor the conditions necessary for life. Many of these exoplanets are thought to have harsh, extreme environments, similar to Venus or even more inhospitable. However, the discoveries on Venus suggest that these planets might still harbor dynamic chemical processes that we have yet to fully understand. If Venus, a planet once considered completely incapable of supporting life, can host complex chemical reactions, then perhaps some of the most extreme exoplanets could also support the formation of complex chemistry and potentially life in ways that we haven't yet imagined. As the research into Venus's atmosphere continues, we are learning more about how planets respond to external chemical inputs. Venus's ability to integrate and transform extraterrestrial material into its atmospheric chemistry provides a model for studying other planets and moons. This dynamic and evolving process will help scientists refine their understanding of planetary evolution, chemical cycles, and the potential for life in extreme environments.
The ongoing study of Venus's atmosphere also raises broader questions about the nature of planetary systems.
We now understand that planets are not isolated systems, but rather dynamic entities that can be influenced by a variety of factors, both internal and external. The interaction between Venus and the material from 3IATLAS is a powerful example of how planets are not static, but instead evolve and adapt in response to their surroundings. This realization has profound implications for the study of other planetary systems and the way we approach the search for life elsewhere in the universe. As we move forward with the study of Venus, one of the most exciting prospects is the possibility of uncovering even more unexpected reactions within the planet's atmosphere. The comet's material, which has already triggered such profound chemical transformations, may be just the beginning. As Venus's atmosphere continues to process these foreign compounds, new chemical pathways may emerge, further altering the composition and behavior of the atmosphere. This ongoing transformation could lead to the discovery of entirely new classes of molecules, reactions, and chemical cycles, and in turn provide valuable insights into the potential for life in other extreme environments. The study of Venus is also helping to refine the methods and technologies that we use to explore other planets. Venus's complex atmospheric chemistry requires a new approach to planetary exploration. Unlike Mars, where the surface is relatively stable, Venus presents an active and dynamic environment, with chemical reactions taking place constantly in its clouds. This makes it an ideal model for studying how planets can adapt to external inputs and how their atmospheres respond to sudden changes. As we continue to study Venus, we will develop new tools, instruments, and techniques that can be applied to other planetary systems, especially exoplanets, which may have atmospheres that are even more extreme than Venus's. This research is not just limited to the study of planetary atmospheres. It has the potential to revolutionize our understanding of fundamental chemistry. The processes that are unfolding on Venus are pushing the boundaries of what we thought was possible in planetary chemistry. The discovery that organic molecules can form and persist in Venus's extreme environment challenges our understanding of how complex chemistry can emerge under harsh conditions. These findings have broad implications for the study of chemistry in general, especially in extreme environments. The lessons learned from Venus could inform the study of other planets, moons, and even asteroids, where chemical processes may be taking place in ways we have yet to fully understand. Moreover, the changes taking place on Venus highlight the importance of interdisciplinary research in planetary science. The interaction between Venus's atmosphere and the comet's material is a complex process that involves chemistry, physics, atmospheric science, and even astrobiology. To fully understand the significance of these changes, scientists from various fields will need to work together, combining their expertise to unravel the mysteries of Venus's atmosphere. This collaborative approach will be essential in advancing our understanding of planetary systems and the potential for life beyond Earth. As we look to the future, the discoveries on Venus provide a new lens through which to view the universe. The study of Venus is not just about understanding this single planet. It is about gaining a deeper understanding of how planets evolve, how chemical reactions unfold in extreme environments, and how life, or the chemistry that leads to life, could potentially arise on other worlds. Venus's unexpected chemical transformations are opening up new avenues for exploration, both in our own solar system and in the search for life on exoplanets. The lessons learned from Venus will shape the future of planetary science and astrobiology,
providing a new framework for studying the dynamic and interconnected nature of the universe. As we continue to study Venus, the unfolding chemical transformations will have lasting effects on our understanding of planetary evolution. The discovery that Venus, a planet once thought to be too hostile for complex chemistry, is now undergoing dramatic chemical changes, challenges the way we think about planetary systems. This is a profound shift in our approach to planetary science, forcing us to reevaluate the conditions under which chemistry can evolve. The cometary material, once thought to simply pass by, has turned out to be a catalyst for transformation, suggesting that planets, even those with seemingly uninhabitable environments, may still harbor the potential for complex chemical reactions. Venus, with its sulfuric acid clouds and extreme heat, has long been viewed as an example of a dead planet. Yet this new revelation, that it is experiencing active chemical evolution, has opened up new possibilities for understanding the behavior of planetary atmospheres. The rapid chemical changes that are taking place in the clouds of Venus indicate that the planet's atmosphere is much more dynamic and responsive than previously thought. This finding challenges the traditional model of planetary chemistry, which assumes that once a planet reaches a certain stage in its evolution, its chemical processes stabilize and remain unchanged. Venus's reaction to the cometary material has shattered that assumption, showing us that planets are capable of adapting to new inputs and evolving over time.
This is a crucial insight because it suggests that even in the most acidic environments, complex chemistry can take place. The fact that these molecules are able to survive and undergo chemical transformations in such an extreme environment has significant implications for our understanding of prebiotic chemistry. If Venus can host such complex reactions, it raises the possibility that other planets and moons with similarly harsh conditions might also be capable of supporting complex chemistry. Another important aspect of this discovery is the impact it will have on the search for life beyond Earth. While Venus is not likely to support life in the traditional sense, the formation of complex organic molecules in its atmosphere suggests that the building blocks of life could be more widespread than previously thought. This discovery provides valuable insight into the potential for prebiotic chemistry to occur in environments that were once considered inhospitable. Moons like Europa, Enceladus, and Titan, with their icy surfaces and subsurface oceans, are now considered more promising targets in the search for life. The chemical processes that are unfolding on Venus could very well be happening on these moons as well in their subsurface oceans or icy crusts. The possibility that life or prebiotic chemistry could exist in these extreme environments is a game changer in the field of astrobiology. The discovery of Venus's chemical transformation also holds implications for the study of exoplanets. As we search for habitable worlds beyond our solar system, the findings on Venus provide a new perspective on what makes a planet suitable for life. Many of the exoplanets that have been discovered orbit stars in the so-called habitable zone, where liquid water could exist on the surface. However, the recent discoveries on Venus suggest that even planets outside this zone with extreme environments could still harbor complex chemistry. This revelation challenges our preconceived notions about what makes a planet habitable and opens up new possibilities for the study of exoplanets. The implications of these findings extend far beyond Venus itself. The discovery that an extreme planet like Venus can still undergo such significant chemical changes challenges many of the assumptions that have shaped our approach to planetary science. The way Venus is responding to the cometary material highlights the incredible adaptability of planetary atmospheres.
No longer can we assume that planets, especially those with seemingly uninhabitable environments, are chemically inert. Instead, we are now witnessing Venus, a planet with one of the most hostile atmospheres in our solar system, actively reacting to external material. This process could be occurring on other planets and moons in our solar system and beyond, reshaping how we think about their potential for supporting complex chemistry and possibly life. What's particularly exciting about the Venusian transformation is the idea that this event could be a model for understanding how other planets with extreme conditions might evolve. In the search for habitable exoplanets, we typically focus on those located in the habitable zone, where liquid water could exist on the surface. But what if the conditions for life, or at least for the chemistry that could eventually lead to life, exist on planets and moons with far harsher environments? Venus shows us that complex chemistry can emerge in places previously considered too extreme for such processes to occur. For example, Europa and Enceladus, two moons of Jupiter and Saturn, respectively, are covered in thick layers of ice, with subsurface oceans believed to harbor conditions suitable for life. Though these moons have environments that are vastly different from Venus's, they share some key similarities, particularly in their capacity for hosting dynamic chemical processes. If Venus, with its crushing atmospheric pressure, high temperatures, and sulfuric acid clouds, can host chemical transformations driven by cometary material, it's possible that Europa and Enceladus may be home to similar processes occurring beneath their icy surfaces. This could have profound implications for our understanding of the conditions under which life could arise, not just on Earth-like planets, but in a much broader range of environments. The case of Venus also raises interesting questions about the role of cosmic material in shaping the chemistry of planets. The cometary material that reached Venus was not only composed of gases, water, and organic compounds, but also refined metals like nickel, which have already started to influence the chemical processes taking place in the planet's atmosphere. This discovery highlights how interstellar material can serve as a catalyst for planetary chemical evolution. The idea that the arrival of an interstellar object can trigger chemical changes in a planet's atmosphere opens up new lines of inquiry for understanding how planets develop over time, especially in cases where planetary systems are influenced by cosmic forces outside their immediate environment. Additionally, the role of sulfuric acid in this chemical evolution is fascinating. As mentioned, sulfuric acid was once considered a simple corrosive agent, too harsh to allow the formation of complex molecules. But now, it's becoming clear that sulfuric acid plays a more dynamic role in Venus's chemistry, potentially helping to preserve and facilitate the reactions of newly arrived molecules. This realization is not just important for Venus, but for the study of other planetary atmospheres with similarly harsh conditions. If sulfuric acid can contribute to the formation of complex molecules on Venus, could it play a similar role on other planets or moons with acidic atmospheres, such as Titan or some of the exoplanets we are discovering?
This new understanding of sulfuric acid and planetary chemistry is one of the many exciting takeaways from Venus's unexpected chemical transformation. Finally, the ongoing study of Venus is also providing valuable lessons about the nature of planetary systems. In the past, we viewed planets as isolated systems that evolved according to their own internal processes. We thought of their atmospheres as self-contained entities, unaffected by external forces. But Venus has shown us that planets are not isolated in this way. They are constantly interacting with the material around them, whether it's cosmic dust, comets, or even material from other planets in the same system. This realization will guide future research into planetary atmospheres, encouraging us to study them as interconnected systems that are subject to a variety of external influences. The new insights from Venus also highlight how planetary evolution can be influenced by seemingly random cosmic events. The cometary encounter that triggered such dramatic chemical changes on Venus was not something that was anticipated, nor could it have been predicted. This randomness, the arrival of interstellar material from outside our solar system, plays a pivotal role in shaping the chemical processes of planets. It forces us to reconsider how external factors like comets, asteroids, or interstellar dust could influence a planet's atmospheric chemistry, and, in the case of Venus, its potential to harbor complex chemistry. This realization challenges our earlier assumptions that planetary systems evolve in isolation, independent of the cosmic forces that surround them. Furthermore, the findings from Venus provide us with valuable lessons for future planetary exploration. As we continue to explore planets and moons across the solar system and beyond, we must consider how these bodies might respond to external influences, especially when those influences come from beyond their immediate environment. Venus's unexpected chemical transformation is a reminder that planets are not static, they are dynamic, constantly evolving systems that interact with the broader cosmos. By studying how Venus reacts to such external forces, we can gain insights into the behavior of other planets and moons, particularly those with harsh environments, like the icy moons of Jupiter and Saturn. The question of whether Venus's transformation could lead to the formation of life is a difficult one to answer. While Venus's extreme conditions may never be conducive to the existence of life as we know it, the formation of complex organic molecules in its atmosphere suggests that the planet may host the fundamental chemical building blocks necessary for life. These molecules may not form life in the traditional sense, but they could be precursors to life, or provide insight into the chemical pathways that might eventually lead to life elsewhere in the universe.
This discovery is an important step forward in our understanding of the potential for life in extreme environments, and raises the question, could other planets or moons with similarly harsh conditions also host prebiotic chemistry, potentially setting the stage for life to emerge in unexpected places? The study of Venus's chemical evolution is also expanding the boundaries of astrobiology. While the conditions on Venus are not suitable for life as we understand it, the recent discoveries show that the building blocks of life, organic molecules, can form in environments previously thought to be too extreme. This knowledge could have profound implications for our search for life elsewhere in the universe. The discovery of similar prebiotic chemistry on other planets or moons could provide a roadmap for understanding how life might emerge on planets with extreme environments, or even in the absence of liquid water. As we move forward in studying Venus, we are also becoming better equipped to study exoplanets, planets outside our solar system that may have environments similar to Venus. The discovery that Venus can undergo such dynamic chemical transformations suggests that exoplanets with extreme conditions might also host complex chemistry. By developing better tools and methods to study exoplanet atmospheres, we can apply the lessons learned from Venus to help us identify potentially habitable exoplanets that may harbor the conditions necessary for life, or at least prebiotic chemistry. This shift in our thinking, from focusing solely on Earth-like planets to considering the potential of extreme worlds, could dramatically change how we approach the search for life beyond our solar system. In the end, the study of Venus has far-reaching implications, not only for our understanding of this planet, but also for the future of planetary science, astrobiology, and the search for life in the universe. Venus, once thought to be an unchanging, hostile world, has shown us that even the most extreme environments can harbor dynamic chemistry and unexpected transformations.
This discovery challenges our assumptions about what is possible in planetary atmospheres and pushes the boundaries of what we know about the evolution of planets, the potential for life, and the interconnectedness of our cosmic neighborhood. As we continue to uncover the mysteries of Venus's atmosphere, one of the most exciting prospects is the potential for future discoveries. The data from the Akatsuki spacecraft and upcoming missions to Venus will continue to provide more detailed insights into how the planet's atmosphere is evolving in response to the comet's material. With each new observation, we move closer to understanding the full scope of the chemical transformations taking place. The lessons learned from Venus's chemical evolution will likely shape the way we explore and understand other planets and moons, not just in our solar system, but also in distant star systems.
The ongoing research on Venus could also help us refine the tools and methods used to study other planets and moons. For instance, missions to moons like Europa or Enceladus, which have subsurface oceans, will need to account for similar chemical processes that we are observing on Venus. If Venus's atmosphere can host the formation of complex organic molecules, similar chemistry could be happening beneath the icy shells of these moons. The technology and techniques developed for studying Venus's atmosphere, along with the data gathered, will provide valuable insight into how to study these distant moons and search for signs of life or prebiotic chemistry in their subsurface oceans. Another fascinating aspect of Venus's transformation is its potential to inspire new theories in planetary science. The changes taking place in Venus's atmosphere challenge many of the models that have been used to understand planetary chemistry. For example, it was once believed that Venus's atmosphere was too harsh for complex chemistry to occur. The new evidence shows that even in such extreme conditions, organic molecules can form and interact. This discovery forces us to rethink the fundamental processes that govern planetary atmospheres and their ability to evolve. As we continue to study Venus, we will likely uncover even more surprising revelations that will push the boundaries of our scientific understanding. Venus's experience with external chemical influences also highlights the potential for cosmic interactions to shape planetary environments. Comets, asteroids, and even interstellar dust could all play significant roles in the evolution of planetary systems. The arrival of material from 3IATLAS demonstrates that planets, even those in the inner parts of the solar system, can be impacted by forces from beyond their immediate vicinity. This realization changes how we view the history of planetary atmospheres and how they are shaped over time. Planets are not closed systems, but are instead dynamic entities that are influenced by the broader cosmos. This cosmic perspective also encourages us to think more broadly about the search for life beyond Earth. While Venus may not be a suitable habitat for life as we know it, its recent chemical evolution suggests that the building blocks of life could emerge in even the most extreme environments. The possibility that Venus's atmosphere is undergoing prebiotic chemistry opens up new avenues for exploring the potential for life elsewhere in the universe. Other planets and moons that seem inhospitable may in fact host the complex chemical processes necessary for life, or at least the chemistry that could lead to life. The study of Venus is a powerful reminder that life, or the conditions for life, may be more widespread across the universe than we previously thought. Finally, Venus's transformation challenges our understanding of planetary habitability.
For years, we have focused on finding Earth-like planets in the so-called habitable zone, where liquid water can exist. However, the discoveries on Venus suggest that habitability could be redefined. Planets with harsh conditions, like Venus, may also be capable of hosting complex chemistry and possibly life in ways that are vastly different from what we have imagined. This realization broadens the scope of our search for life beyond Earth and encourages us to consider new types of environments that may harbor life, both in our solar system and on exoplanets orbiting distant stars. The study of Venus's transformation is not only expanding our understanding of the planet itself, but is also reshaping the entire field of planetary science. The way Venus is reacting to the external influence of the comet's material is forcing us to rethink the dynamics of planetary atmospheres and how they evolve over time. This unexpected event has introduced new variables into our models, showing us that planetary systems are more interconnected than we ever realized. No longer can we assume that a planet's atmospheric chemistry is isolated from external forces. The interaction between Venus and 3IATLAS demonstrates that planets are active systems, constantly evolving in response to their environment, whether that environment is influenced by internal geological processes or external cosmic forces. This understanding has far-reaching implications, not just for the study of Venus, but for the study of all planetary systems. As we observe Venus's chemical changes, we are learning how planets respond to external inputs, a lesson that will be invaluable in the study of other planets, moons, and even exoplanets. For example, moons like Europa and Enceladus, which are believed to have subsurface oceans, could be subject to similar processes, where external materials, such as comets or cosmic dust, could play a role in shaping their chemical environments. If Venus's atmosphere can undergo such transformations from a single encounter with interstellar material, could other bodies in the solar system also experience similar chemical evolution? This is a new avenue of exploration for planetary scientists and astrobiologists alike. The discoveries on Venus are also prompting us to reconsider how we define habitability. In the past, we have focused on finding planets with Earth-like conditions, assuming that liquid water and a temperate climate were the primary prerequisites for life. However, Venus shows us that life, or at least the complex chemistry that could lead to life, might not be limited to Earth-like environments. The fact that Venus, with its high temperatures, sulfuric acid clouds, and intense atmospheric pressure, can still undergo significant chemical changes, challenges our assumptions about what makes a planet habitable.
It opens up the possibility that life, or the chemistry necessary for life, could exist in environments that were once considered too extreme for such processes. In the search for life beyond Earth, these findings are a game changer. The discovery that Venus's atmosphere is capable of supporting the formation of organic molecules and other complex compounds suggests that the conditions for prebiotic chemistry may be more widespread than previously thought. The same processes that are unfolding on Venus could potentially occur on other planets or moons in the solar system, and even on exoplanets in distant star systems. This broadens the scope of our search for life and encourages scientists to think beyond Earth-like planets when considering where life might arise. Moreover, the transformations occurring on Venus are not just about life, they are also about understanding how planets evolve over time. The fact that Venus's chemical system is actively adapting to new inputs demonstrates the dynamic nature of planetary systems. This discovery is a reminder that planetary environments are not static, but constantly in flux, influenced by both internal and external factors. Venus, once thought to be a chemically inert world, is now showing us that even planets with extreme environments can undergo chemical transformations, potentially altering their atmospheric composition and evolutionary trajectory. As we continue to study Venus, we are also gaining a better understanding of how to explore planets and moons with extreme conditions. The data from Akatsuki and future missions will provide valuable insights into how planets respond to external influences, and these insights will help guide future planetary exploration. By studying Venus, we are learning how to design missions that can detect and study the chemical processes taking place on planets and moons with harsh environments. This will be crucial for studying exoplanets, many of which are located in environments vastly different from Earth's. The discoveries on Venus will help us refine the tools and techniques we use to study these distant worlds.
increasing our chances of discovering new chemical processes and, potentially, signs of life. The study of Venus's transformation also underscores the importance of ongoing research and collaboration in planetary science. The unexpected chemical evolution taking place on Venus demonstrates that planetary systems are far more complex and dynamic than we initially realized. It's crucial that we continue to expand our understanding of how planets interact with external material and how their atmospheres respond to cosmic influences. The findings from Venus will undoubtedly inspire further research not just on this planet, but on other celestial bodies that share similar conditions or histories.
As we continue to observe Venus and other planets in our solar system, the lessons learned from this cometary encounter will guide the design of future missions. Spacecraft such as NASA's Veritas, Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy, and ESA's Envision will provide critical data on Venus's surface and atmosphere, helping us to better understand the long-term effects of the comet's arrival and the ongoing chemical processes. These missions will help refine our models of planetary evolution and atmospheric chemistry, providing key insights into the dynamic nature of planetary systems and the potential for life or prebiotic chemistry on other worlds. In addition to refining our understanding of Venus, these missions will also provide the groundwork for studying exoplanets and their atmospheres. As we discover more exoplanets in different star systems, the lessons learned from Venus will help us to identify potential candidates for further study. Many of these exoplanets exist in extreme environments that were previously thought to be inhospitable to life. However, the discoveries on Venus suggest that life, or at least the chemistry that could lead to life, may be possible in even the most extreme conditions. Venus's transformation challenges our assumptions about what makes a planet habitable, and these new insights could be crucial in identifying new, unexpected environments where life could arise. The transformation of Venus's atmosphere also raises important questions about the nature of planetary habitability and the potential for life elsewhere in the universe. Traditionally, scientists have focused on finding Earth-like planets in the so-called habitable zone, where liquid water could exist on the surface. However, the discoveries on Venus suggest that planets outside the habitable zone, with extreme conditions, might still harbor the necessary conditions for complex chemistry, or even life. Venus's ability to support the formation of organic molecules, even in such a harsh environment, opens up new possibilities for the search for life. It suggests that the conditions necessary for life, or at least prebiotic chemistry, may be more common in the universe than we once believed. This realization has broad implications for astrobiology and the search for extraterrestrial life. As we explore more planets and moons in our solar system and beyond, we will need to consider a wider range of environments in our search for life. Venus's experience provides a crucial model for how life, or the chemistry that could lead to life, might exist in environments that were once considered inhospitable. The discovery of complex chemistry on Venus reminds us that life could emerge in places we once thought too extreme to support it, challenging our narrow definition of habitability and opening new avenues for exploration.
The ongoing exploration of Venus is a testament to the unpredictable nature of planetary science. Venus, once viewed as a planet beyond the reach of complex chemical processes, is now revealing its dynamic and ever-changing atmosphere. The cometary event that triggered these transformations is a reminder that even the most hostile planets in our solar system can still hold surprises. The discoveries on Venus challenge our previous assumptions about the limitations of planetary environments and show us that planets are not static, but rather evolving systems. What's especially fascinating is that Venus is not alone in its potential for chemical evolution. This event on Venus opens the door for further research into how other planets in our solar system and beyond might be affected by external forces. For example, Jupiter's moon Europa, which has a subsurface ocean beneath its icy crust, may undergo similar chemical reactions when influenced by external material, such as comets or meteoroids.
The idea that such interactions could trigger complex chemistry, even on icy moons, is an exciting frontier for astrobiology. Just as Venus has shown us that even the harshest environments can be chemically active, other moons and planets may also harbor hidden chemical processes that we are only beginning to uncover. Furthermore, the findings on Venus highlight the importance of external material in shaping planetary environments. While it has long been understood that comets and asteroids can introduce new elements into a planet's atmosphere, the extent to which these materials can alter the chemistry of a planet's atmosphere was previously unclear. The comet's influence on Venus has shown that these cosmic materials can have far-reaching and long-lasting effects. This realization is important not just for studying Venus, but also for understanding the history and evolution of other planetary systems. It adds a new layer of complexity to our models of planetary chemistry, showing us that planets are shaped not only by internal processes, but also by interactions with the wider cosmos. As our understanding of Venus deepens, we are also refining our approach to studying exoplanets. The discovery that a planet with extreme conditions can still undergo such significant chemical transformations will change the way we look at distant worlds. Venus's ability to form complex molecules, despite its sulfuric acid clouds and high temperatures, challenges our assumptions about the necessity of Earth-like conditions for life to emerge. It encourages us to look beyond traditional models of habitability and consider the potential for life for prebiotic chemistry on planets with more extreme environments. The implications for the search for life are profound. For years, the search for habitable planets has focused on those that fall within the habitable zone of their stars, where liquid water can exist on the surface.
However, the findings on Venus suggest that life, or at least a chemistry that could lead to life, may be possible in environments that were previously deemed too harsh. This opens up new possibilities for the search for life beyond Earth as we begin to consider planets and moons that are vastly different from Earth in their conditions, but may still harbor the conditions for complex chemistry. Venus's transformation also serves as a reminder of the importance of continuing to push the boundaries of our exploration and understanding. Even in an era of advanced space missions, there is still so much we don't know about the planets and moons in our own solar system, let alone the countless exoplanets scattered across the galaxy. Each discovery, whether it's the chemical changes occurring on Venus or the unexpected presence of organic molecules, teaches us something new about the universe we live in. These revelations not only expand our knowledge of our solar system, but also lay the groundwork for future missions to other planets and moons, bringing us ever closer to answering the big questions about the potential for life in the cosmos. As we continue to explore Venus, one of the key questions that remains is how the planet's atmosphere will evolve in response to the cometary encounter. The transformation that has already taken place suggests that Venus's atmosphere is far more dynamic than we previously thought. The comet's material has introduced foreign molecules into the Venusian atmosphere, and the resulting chemical reactions are still ongoing. These reactions are not only altering the composition of the atmosphere, but also opening up new avenues for studying planetary chemistry. The changes we're observing on Venus are pushing the boundaries of our understanding of how planetary atmospheres work, and these findings could lead to the development of new models for planetary chemistry in general. As scientists continue to study the data coming from Venus, it's becoming clear that the impact of the comet is not just a brief and isolated event, but rather a long-term process that will continue to unfold over time. This raises the question of whether Venus will eventually reach a new equilibrium, or if the changes initiated by the comet will continue to ripple through the atmosphere for years to come. The chemical processes occurring on Venus right now are far from simple. They involve a complex interplay between foreign molecules, existing atmospheric components, and the planet's unique environmental conditions.
This dynamic, ongoing transformation will require years of study to fully understand, and it promises to uncover new insights into the behavior of planetary atmospheres and the potential for life elsewhere in the universe. One of the most intriguing aspects of this transformation is how Venus's atmosphere is responding to the introduction of organic molecules.
The presence of hydrogen cyanide, a molecule that is a precursor to amino acids, is especially significant because it suggests that the building blocks of life could be forming in Venus's atmosphere. While this does not mean that life is emerging on Venus, it does mean that the chemical processes necessary for life, or at least for prebiotic chemistry, are taking place in an environment that was once considered too extreme for such reactions to occur. This discovery has profound implications for the study of astrobiology and the search for life beyond Earth. If Venus's atmosphere can host the formation of complex organic molecules, it opens up the possibility that other planets and moons in our solar system and beyond could also host the necessary conditions for life or prebiotic chemistry to emerge. The implications of this discovery extend far beyond Venus. As we look at exoplanets, planets in other star systems, we must reconsider our traditional definition of habitability. For years, the search for life has focused primarily on planets in the habitable zone, where liquid water can exist on the surface. However, the findings on Venus suggest that life, or at least the chemistry that could lead to life, may be possible on planets with harsh conditions, even those that are not in the traditional habitable zone. This opens up a new frontier in the search for life beyond Earth. Planets with extreme environments, like Venus, might be capable of hosting complex chemistry and potentially life in ways we have not yet considered. This realization broadens the scope of the search for life and forces us to think more creatively about where life might exist in the universe. In addition to its implications for the search for life, the study of Venus's transformation also sheds light on the evolution of planetary systems. The cometary encounter has disrupted the long-standing chemical equilibrium of Venus's atmosphere, providing a glimpse into how planetary systems can change over time. This event challenges the assumption that planets evolve in predictable, steady states. Venus's transformation shows us that planetary atmospheres are not static, they are dynamic and can be influenced by external forces in unexpected ways. This realization is crucial for understanding how planetary systems evolve over long timescales and how they might respond to future cosmic events. It also raises the question of whether other planets in our solar system, like Earth, could experience similar transformations in the future, driven by external factors like comets or asteroids. The ongoing transformations on Venus are a stark reminder of the complex and dynamic nature of planetary evolution. We've long considered planets like Venus to be examples of extreme environments where little to no chemical change occurs beyond what is driven by internal processes.
However, the cometary encounter has shown us that planetary systems can be far more susceptible to external influences than previously imagined. As we continue to study the data from Venus, we are learning that planets can change rapidly when exposed to foreign materials, and that these changes can have lasting effects on their atmospheric chemistry. The case of Venus also provides valuable lessons for the future exploration of exoplanets. As our understanding of planetary chemistry deepens, we will be able to apply these insights to the study of planets beyond our solar system. Exoplanets, many of which are located in extreme environments that we once thought uninhabitable, could harbor similar chemical reactions triggered by external influences. The realization that a planet's atmosphere can undergo profound chemical changes from the interaction with interstellar material opens up a new paradigm for how we think about exoplanets and their potential to support life or complex chemistry. In the future, the study of Venus's atmosphere will continue to inform the design of missions to other planets and moons. As we look to study moons like Europa, Enceladus, or Titan, which have subsurface oceans or thick atmospheres, we must consider how these bodies might react to similar external forces. The cometary event on Venus demonstrates that the arrival of external material can trigger dramatic chemical changes, and similar events on moons or exoplanets could lead to new discoveries about the potential for prebiotic chemistry or life. The tools and techniques developed to study Venus will provide a foundation for future missions to other celestial bodies, allowing us to better understand how planets and moons with extreme environments can evolve and respond to external influences. One of the most exciting aspects of Venus's transformation is the potential for future discoveries. As more data is collected, scientists will be able to observe how the chemical reactions that began with the comet's arrival continue to unfold. It's possible that even more complex reactions will occur as the foreign molecules continue to interact with Venus's atmosphere. This could lead to the formation of entirely new compounds and potentially even new forms of chemistry that have never been seen before. These findings will not only deepen our understanding of Venus, but will also contribute to the broader field of planetary science as we begin to understand how planetary systems evolve and adapt to new chemical inputs. This ongoing research into Venus's atmospheric changes is also reshaping our understanding of the broader processes that govern planetary habitability. For decades, scientists have focused on finding planets that resemble Earth, assuming that liquid water and a temperate climate are the key ingredients for life. However, Venus's chemical transformation has shown us that planets with extreme conditions can still harbor complex chemistry.
This challenges our preconceived notions about what makes a planet habitable and encourages us to think more broadly about the potential for life in the universe. The search for life may not be limited to Earth-like planets, but could extend to worlds with extreme environments where the necessary chemical reactions can take place. As the data continues to flow from Venus and the analysis of its atmosphere deepens, we will continue to refine our models of how planets respond to cosmic influences. Venus has shown us that external factors, such as the arrival of interstellar material, can radically alter a planet's atmosphere. In the case of Venus, this event has triggered a series of chemical reactions that are still unfolding, offering a real-time example of planetary chemistry in motion. The discovery that a planet with such an extreme environment can undergo this kind of transformation raises important questions about the role of external forces in planetary evolution. What other types of material from beyond our solar system might affect planets and moons in similar ways? How common are these kinds of interactions across the galaxy, and how might they influence the evolution of planetary systems? The study of Venus also sheds light on how planets, even those in the most inhospitable environments, may harbor dynamic chemical systems. In the case of Venus, it was once assumed that the planet's atmosphere was too harsh to allow for the formation of complex organic molecules. Yet, the comet's material has introduced the building blocks of life into the atmosphere, suggesting that complex chemistry can occur in even the most extreme conditions. This discovery challenges the notion that only Earth-like planets can harbor prebiotic chemistry or potentially life. If Venus can undergo such dramatic chemical transformations, then other planets and moons in our solar system and beyond may also be capable of supporting similar processes, even if they exist in harsh, seemingly lifeless environments. This opens up new possibilities for the search for life on other planets. As we focus on studying exoplanets, particularly those in the so-called habitable zone, we must also consider planets and moons that fall outside this zone. Venus, as well as the icy moons of Jupiter and Saturn, show us that habitability can be defined in many ways. Instead of focusing solely on Earth-like conditions, we must begin to explore the potential for life in a wider range of environments. The discovery that organic chemistry can unfold in extreme conditions on Venus is an exciting step forward in this direction, as it broadens the scope of the search for life beyond Earth. Looking ahead, the study of Venus's chemical evolution will also help us refine the tools and technologies used to study other planets and moons.
As we develop better techniques for studying planetary atmospheres, we will be able to apply the lessons learned from Venus to the exploration of exoplanets. For example, the upcoming James Webb Space Telescope, the JWST, will allow us to analyze the atmospheres of distant exoplanets in unprecedented detail. By understanding the chemistry of Venus and other planets in our solar system, we will be better equipped to interpret the atmospheres of exoplanets and identify signs of prebiotic chemistry or potential life. In addition, the study of Venus has important implications for understanding the history and future of Earth. Venus's transformation serves as a reminder that planetary systems are not static. They evolve over time, sometimes in unpredictable ways. The changes currently happening on Venus could provide us with clues about how Earth might change in the future, particularly as it is influenced by cosmic forces. Understanding how Venus's atmosphere is adapting to external influences could offer valuable insights into how Earth's atmosphere might respond to similar events. This could help us better prepare for potential future challenges, such as the impacts of climate change, asteroid strikes, or other planetary-scale phenomena. As we reach the conclusion of our exploration of Venus's chemical transformation, it's clear that this discovery is just the beginning of a much larger story. The changes happening in Venus's atmosphere are not only reshaping our understanding of this particular planet, but also redefining the way we think about planetary evolution, the potential for life beyond Earth, and the role of external influences in shaping planetary systems. Venus, once thought to be an unchanging, hostile world, has now become a dynamic, evolving system, offering us valuable insights into how planets can adapt to new materials and how their atmospheres can be influenced by cosmic forces. This revelation opens up new avenues of exploration for scientists, encouraging them to consider the potential for life and complex chemistry on planets and moons with extreme environments. The discovery that Venus can host complex organic chemistry, despite its extreme conditions, is a powerful reminder that life, or at least the chemical building blocks for life, could exist in unexpected places. As we continue to study Venus, we will not only learn more about the planet itself, but we will also refine our search for life on other worlds, expanding the boundaries of what is considered habitable and opening up new possibilities for astrobiology. In the broader context of planetary science, Venus's transformation has also shown us that planets are not isolated systems. The comet's material, which arrived from beyond our solar system, has been incorporated into Venus's chemistry, demonstrating that planets are not merely shaped by internal processes, but are also subject to the influences of the broader cosmos.
This realization will be crucial for future research into planetary systems as we continue to explore how external factors can affect the evolution of planets and their atmospheres. In the coming years, the study of Venus will undoubtedly lead to further discoveries. As new missions to Venus and other planets are launched, the data gathered will continue to expand our understanding of planetary evolution and the potential for life in the universe. The transformation of Venus's atmosphere is a profound reminder that the universe is full of surprises, and that the search for life, complex chemistry, and planetary change is only just beginning.